Testing, testing. Alright, we're recording. Okay. Alright, non-resident training course, September 1998, Navy Electricity Electronic Training Series, Module 18, Radar Principles, Navy EDRA 141190. Distribution Statement, Approved for Public Relations Distribution Unlimited. Let's see here. Alright, Chapter 1, Radar Fundamentals. Chapter 2, Radar Subsystems. Chapter 3, Radar Indicators and Antennas. Chapter 4, Radar Systems and Maintenance. Alright, the following text is this course. While you the technical manuals associated with the equipment you will be working with, you will find below the notations that some of the paragraphs notations are easy to emphasize here has exist and care must be taken and observed. Warning and operation procedure practice with the condition which may be resolved with injury or death to carefully, if not carefully, follow caution and operating procedure practice with the condition which may result with damage to the equipment not carefully observed or followed. Note, operating practice or procedure practice condition which is essential to emphasize. And then Chapter 1, Learning Fundamentals, our learning objectives. Radar fundamentals, learning objectives. Learning objectives are stated with the beginning of each of the chapter. Learning objectives serve for the preview information you're expected to learn in the chapter. The comprehensive check questions are based on the objective by successfully completing the OCC, ECC. You indicate that you have met the objective that you learned in the information learning objectives listed below. Define range bearing altitude as they relate to the radar system. Discuss how pulse with peak power and beam with effect with the radar performance. Discover the factors contributing in order to track from radar accuracy. Use the block diagram. Discover the basic function, principle, operation, and relationship with the basic unit of the radar system. Explain various ways in which the radar system are classified, including standard Army Navy classifications. Explain basic operation of the continuous wave pulse or Doppler radar systems. Introduction. The term radar is common in today's everyday language. You probably use yourself with referring to method of recording the speed of the movement of recording the speed of the moving object. The term radar is an acronym made up of the radio detection ranging. The term is referred to the electronic equipment to detect with the presence of the direction, with the height, with the distance of the objectives by using reflected electromagnetic energy, frequency of the radar, unaffected with the darkness, and also penetrates weather to some degree, depending on the frequency of the perimeter of the radar system to determine the position of the ship, the planes, the land masses that are invisible to the naked eye because of the distance and darkness of the weather. The development of the radar is a highly complex system with today's represent the accumulated developments. Many people and nations. General principle of the radar have been known for a long time by any of the but many electronics discovery been necessary before the use of the whole radar system could be developed. World War II provided a strong incentive to develop practical radar. Early versions were soon after the war began. Radar technology has improved with the years since the war, and we now have the radar system with a smaller, more efficient, but better than those earlier versions. Modern radar, the early detection of the surface of the air objects, provide extremely accurate information, distance, direction, height, speed of the object's radars used to guide missile targets directing with the firing of the gun system. Other types of radars provide long-distance surveillance navigation information. Basic radar concept. The electronic principle of the radar operates with very similar to the principle sound wave reflection. Show the direction of the sound wave reflection object like a rocket cannon or cave. You will hear an echo. You will if you know the speed of the sound in the air, you can estimate the distance and general direction of the object. Time required for the return echo roughly converted with the distance if the speed of the sound is known. Radar uses electromagnetic energy pulse in much the same way. Shown in Figure 1, the radio frequency energy is transmitted to it and reflects from the reflecting object, and a small portion of the energy is reflected and returned to the radar. So the return in energy is called an echo. Just in sound terminology, radio sets uses echo to determine the direction and distance of the reflecting object. Show the reflecting target, the echo, the electromagnetic energy pulse, the radar echo. Note that these terms, the target, return, echo, contact object, and reflecting object, use the interchangeable throughout the model to indicate the surface of the airborne object that has been detected by radar system. Radar system also have the characteristics common with the telescope that provide only with a limited view of the field of view with the required reference coordination system to find the position of the detected object. Describe the location of the object you can see with it through a telescope. You will most likely refer to the prominent feature of the land. Radar requires a more precise reference system. The radar surface with the angular measurement of the normally made with a clockwise direction from true north is shown in Figure 1-2 with the from the heading of the shipping aircraft with the surface of the earth is presented in an imaginary flat plane. Tangent or parallel to the Earth's surface at that location, the plane is referred to as the horizontal plane. All angles in the up direction are measured with the secondary imaginary plane that is perpendicular to the horizontal plane. This shows your radar reference coordinates: the true north, the true bearing, the range, the elevation angle, the vertical plane, and the horizontal plane. The second plane is called the vertical plane radar location center of the coordinate system, and this line radar system detects for the object referred to the line of sight. The length of this line is called the range. The angle between the horizontal plane and the line of sight is called the elevation angle. The angle measured with clockwise to the true north of the horizontal plane is called the true bearing or azimuth angle. Three coordinates with the range, bearing, elevation describe the location of the object with respect to the antenna. The range radar measurement, the range distance with the many possible to cover the property to radiate with electromagnetic energy. The energy normal travel through the space of a straight line. The coordinate constant speed will vary slightly because of the atmospheric weather conditions. The effect of the atmospheric weather have on the energy that we'll discuss later in this chapter. However, for this discussion on determining the range, the effect will be temporarily ignored. Electromagnetic energy traveled with the approximate speed of light with 186,000 statute miles per second. The Navy of the nautic mile with the calculated distance of 180,000 statute miles and approximately 162,000 nautical miles. With the distance for the statute mile is approximately 5,280 feet. The distance for the nautical mile is approximately 6,080 feet. Radar timing is usually expressed with the microsecond with the relate with the radar timing distance traveled with the radar energy. You should know that the radiating energy radio set traveled approximately 984 feet per microsecond. With the knowledge for the nautical mile is expressed in 6,080 feet. With you configure the approximate time required for the radar energy travel to 1 nautical mile. You do the following calculation: time of the energy travel to 1 nautical mile is 6,080 feet over the 984 feet per microsecond. That gives you 6.18 microseconds approximately. Same answer can be used with the yards instead of the feet. The following calculation: 6,080 feet with approximation nautical miles converted in 2,227 yards. Energy speed changed to 980 feet to 328 yards per microsecond. Is the time of the energy traveled over the 2,027 yards with over 328 yards per microsecond. The nautical mile 6.18 microseconds. The pulse type radar transmit the short bursts of electromagnetic energy. Target range determine the measuring with the ellipse time with the pulse of the travel and to the return with the target. The the two-way travel is involved the whole time. The 12.36 to 6.182 microseconds per nautical mile with the elapse between the start of the pulse of the antenna and return of the antenna from the target. The figure 12 to 36 of the microsecond time travels intervals, sometimes referred to as the radar mile, radar nautical mile, nautical radar mile. The range of the nautical mile to objective can be found with the measuring ellipse time. During the round trip, the radar pulse dividing the quantity of the 12.36 for the equation form is range is equal to the elapsed time over 12.36 microseconds per nautical mile. For example, the elapsed time of the echo of 62 microseconds, distance of the 5 miles is shown in the following calculation. Range of the elapsed time over 12.36 microseconds per nautical mile, or 62 microseconds over 12.36 microseconds per nautical mile, gives you 5 nautical miles approximately. Note, unless otherwise stated, the distance will be expressed in nautical miles throughout this module. Minimum range. Recall that in each module 11, the microwave principal duplex or alternator switching the antenna between the transmitter and receiver. The only one antenna may need to be used. The switching necessary because of the high power pulse with the transmitter would destroy the receiving the radio frequency energy. We're allowed to enter the receiver that is probably already realized that the timing of the switching action is critical to the operation of the radar system. While you may not realize the minimum range and ability of the radar system is affected by the timing. The two most important times is action of the pulse with the recovery time. The time action must be such that during the transmitted pulse with and only the transmitter can be detected with the antenna. Immediately after the pulse is transmitted, the antenna must be reconnected. The leading edge of the transmitted pulse with the cover of the duplexer again to align with the antenna of the transmitter. The action is essentially instantaneous. The end of the transmitted pulse of the trailing edge of the pulse of the cover of the duplexer to align with the antenna with the receiver. However, the action is not instantaneous. A small amount of the time elapses at the point with referred to as the recovery time. Therefore, the total time with the while the receiver is unable to receive the reflected pulse is equal to the pulse with the plus for the recovery for the time. Not any of the reflected pulse with the close of the target returning from the receiver is connected to the antenna will be undetected. The minimum range in yards at which the target can be detected is determined using the following formula: pulse width recovery time as expressed within microseconds or fractions of the microsecond. Minimum range and pulse width plus for the recovery time divided by 2 times 328 yards. Minimum range pulse width times recovery equals 1 times 164 yards. For example, the minimum range of the radar system of the pulse of 25 microseconds and the recovery time of the 1/10 of a microsecond is figures 25 plus 0 to 1 times 164 is 4,168 yards. Most modern radar systems designed with a small recovery time, but the figure can often be ignored figuring the minimum range. Your maximum range. The maximum range of the pulse radar system depends on the carrier frequency, the peak power of the transmitted pulse repetition frequency, pulse repetition rate, with the receiver sensitivity, pulse repetition frequency, primary limiting factor, the peak power of the pulse to determine the maximum range of the pulse can travel to the target and still return with a usable echo, and use an echo to the small signal detectable by the receiver system that can be processed and presented on the indicator. The frequency of the radio frequency and the pulse rate of the radar is referred to the carrier frequency of the radar system. The carrier frequency is often limited to the fact that the maximum range capable of the radar system to pick up the radio frequency energy above 3,000 megahertz is rapidly actuated by the atmosphere. The creep of the usable range of the radar frequency energy therefore, as of the carrier of the frequency is increased, the transmitted power must be also increased to cover the same range. The long range covered is more easily achieved with the lower frequency of the atmosphere conditions have less effect on the lower frequency energy. Radar system radiate each of the pulse of the carrier frequency during the transmitted time, waiting for the return echo during list for the rest of the time of the radiated second pulse, as shown figure 1-3. The number of the pulse radiated in 1 second is called the pulse repetition frequency. The pulse repetition rate at the time of the or the pulse repetition rate. The time between the one pulse over the next pulse of the call for the pulse repetition time is equal to the reciprocal of the pulse repetition frequency as follows. The pulse repetition time is equal to 1 over the pulse repetition frequency, the pulse width, the listing time, and the pulse repetition time, radar pulse relationships. Ambiguous return for the radar time system that must reset to 0 each time of the pulse of the radiative distance for the radar ranging detect for the measure of the time 0 for the each of the time of this of the phase rate repetition time phase repetition time of the radar because within important maximum range determined because of the target return with the time exceed with the pulse repetition time. Radar system approximately incorrect location range with the radar screen. The return with the incorrect range is referred to the ambiguous return second sweeps echoes. Figure 1-4 illustrates the radar system with a 1 millisecond pulse rate time. As pulse is shown on the top of the example, the two transmitted pulses hitting the target of the return are shown on the bottom, and then K for the target with the A from the whole of the travel round trip over the 5 milliseconds, which will equip the target range of 82,000 yards. And since the 5 milliseconds is less than 1 millisecond of the display with the correct range, no problem. However, the target B is 1,968 yards. Distance over the yard system, and in this case, the total pulse travel time is 1.2 milliseconds. Exceed the phase repetition, pulse repetition limitation for the 1 millisecond for this rate of the first transmitted pulse for the traveling with the due in return for the target B. Second pulse is transmitted with the radar system is reset to 0 again. The first pulse of the target B continued with the journey back with the radar system, but arrived during the timing the period of the second pulse. Result of the inaccurate reading, in this case, the first return pulse from the target B with arrived at 2 milliseconds, or 2/10 of the millisecond into the second timing period. The result of the range of the 32,800 yards instead of the actual 196,800 yards. You should see the example of the pulse return with excess of the pulse repetition time of the radar system. A result of the ambiguous range below the pulse return with the pulse repetition time limits results in normal unambiguous range of the maximum unambiguous range of the given radar system can be determined by the following. Radar maximum ambiguous is 162,000 miles a second over 2 with the pulse repetition time. Pulse 1, pulse 2, pulse repetition time 1 millisecond, half a millisecond, 82,000 yards, target 82,000 yards, 1.2 millisecond, target 1,968 yards, ambiguous. Alright, pulse repetition frequency and power calculation. Energy content with the continuous wave radar transmit may easily figure because the transmitter operates continuously. However, the pulse radar transmitter are switched on and off to provide the range timing the information each of the pulse. The resulting waveform of the transmitter shown figure 1-3 with the amount of the energy waveform and the because of the maximum range detected relate with the transmitter output power. More energy with the radar system transmit the greater target detection range will be. The energy content of the pulse is equal to the peak's maximum power level of the pulse multiplied by the pulse width. However, the meter uses the power the radar system to do so over the period of time is longer than the pulse width. For this reason, the pulse repetition time is included in the power calculation transmitter. Power measured over such a period of time is referred to as the average power. With figure 1-5 illustrates the way of the average power would be shown with the total energy content of the pulse. Shaded areas represent the total energy content of the pulse to the crash hatch area with the represent the average power equal to the peak power spread out over the pulse repetition time. Keep in mind that you find with the figure 1.5 that no energy is actually present between the pulse and the pulse radar. The figure drawn, they just shown how the average for the power is calculated with the pulse repetition time. You have to help figure the average power, to be able to define with the whole time at the beginning of the one pulse, at the beginning of the next pulse. Average power is followed. The power average power is peak power, pulse width, and pulse repetition time. Pulse average power is equal to the pulse peak power times the pulse width over the pulse repetition time. Show that the peak power pulse width average power next pulse time of the pulse repetition time. Because the one part of the pulse repetition time is equal to the pulse repetition frequency, the formula may be written as follows: the pulse average is equal to the peak power times the pulse width times the pulse repetition frequency. Product of the pulse width with the pulse repetition frequency and above the formula is called the duty cycle of the radar system. The duty cycle of the ratio of the time on and time off of the transmitter shown in figure 1.6. Duty cycle is equal to calculate both the peak power and average of the power of the radar system. The formula the duty cycle is shown below. The duty cycle is equal to the pulse width at the time the pulse rate repetition frequency. So pulse repetition frequency with the pulse repetition rate with the interchangeable terms. Total time of the pulse width at the time off of the pulse repetition time. The sum of the duty cycle of the radar is usually known, but the most common formula average power is expressed as peak average pulse average with the peak equal to the peak time of the duty cycle of the transposing above the formula with the common formula for the peak power. Peak is equal to the power average over the duty cycle. The peak power that must be calculated more often than the average power. This because the previously mentioned the most measurement instruments measure average power directly. An example is shown below. Power average is 20,000 watts. Peak pulse width is 20 microseconds, and pulse repetition frequency 1,010 pulse per second. And the peak for PP, you must figure the duty cycle is duty cycle equals the pulse width times pulse repetition frequency. You get 200ths of a second for the duty cycle. Now you have the duty cycle. The pulse the pulse may be calculated as follows: peak is equal to the peak average over the duty cycle is 20,000 over 200 is equal to 1 million, or 10 to the 6 watts. Antenna height and speed. The another effective effect of the radar reading of the antenna height of the radio frequency of the energy transmitted by the radar system travel the straight line that does not normally bend. Confirmed the curve of the air of the height and the of the antenna target the air with the fact that the detection rate, the distance of the horizontal and nautical mile with the radar system varies with the height of the antenna according to the following formula. Radar horizontal distance in nautical miles is equal to 1.25 over the time of the square root of the antenna height in feet. For example, assume the antenna height of 64 feet. In the calculation, the horizontal distance would be 1.25 times the square root of the 64 would be 1.25 times 8 of the 10 nautical miles. Our target range greater than the radar horizon will not detect it unless it has high enough to be above the horizon. Example of the antenna target height with the relationship with the phone figure 1.7. The own ship with the radar horizon line of sight with the ocean surface of 3,000 feet. Ship below the horizon horizon will not be detected. The antenna rotation always affects the maximum detection range. Slower antenna rotate with the greater of the detection range of the radar system. The antenna is rotated at 10 revolutions per minute. The beam energy strike with each of the target the 1/2 of the time, and it would be rotation with the 5 repetitions per minute. The number of strike for the per antenna revolutions referred to the hits per second, and does during each of the revolutions enough alpha to be transmitted to return the usable echo. The more pulses transmitted to give an area with a slower antenna speed, the greater the number of the hits per scan. Example of the antenna rotate 20 RPMs, they complete with the 3 revolutions, 3 seconds. During this time, the transmitter with the pulse repetition frequency of the 200 pulse per second. The transmits 600 pulses. Since 360 degrees of the azimuth, it must be covered with the following formula show with the number of pulses each degree of the azimuth. 600 pulses per revolution over 360 degrees per revolution equal to 1.6 pulse a degree. Such low number of pulses to give the target with a greatly number increases the likelihood of some of the targets being will be missed entirely. Therefore, the pulse repetition frequency and antenna speed must be matched with maximum efficiency. All right, the bearing. The true bearing reference for the true north and radar targeted angle between the true north and the line pointed directly within the target with the angle is measured with the horizontal plane within the clockwise direction of the true north. Bearing angle with the radar targeted may also be measured in the clockwise direction of the center line on within your own chip of the aircraft referred to with the relative of the bearing. Both true and relative of the bearings are illustrated in figure 1.8. So the true north own chip, the true bearing at 90 degrees relative to the bearing, and 45 degrees target and ship center line. The antenna of the most radar system designed with the radiate energy, one direct lobe of the beam can be moved with the bearing simply with the moving the antenna. As you can see in Figure 1.9, shape of the beam is such for the echo, the strings, echo signal strength with the barrier, the amplitude of the antenna beam with the move of the crown of the target. The antenna position A, echo is minimal, with the position B, the beam axis is pointed directly at the target. The echo strength with the maximum of the bearing angle of the target that can be obtained by moving the antenna to the position of the echo strength with the actual practice for each for the radar antennas move continuously. Point of the maximum each return is determined by a detection circuit as the beam passes the target or visually by the operator. The weapon control the guide for the radar system of our position of the point. Maximum signal return maintained with the position either manually or by automatic tracking circuit. Show of the antenna in position A, signal strength of the antenna target in the direction of the rotation lobe axis, signal strength lobe axis target angle position B, altitude. Many radar systems are designed to determine only the range and bearing of the objects of the radar systems are called the two-dimensional radar. For the most case of the system, the further described in the search radar system functions. Earlier warning devices converge over the fixed volume of the space of the range bearing the coordinate to provide each of the information plate for the target in the general area with respect to the radar, so to determine the distance, direction of the travel, the relative speed. However, when the action must be taken again, so the airborne target altitude must be known as well. The search of the radar system to detect the altitude as well as as the range bearing through the three-dimensional radar, the altitude, the height finding with the search radars, using a very narrow vertical plane with a beam and scan with the elevation mechanically, electronically to pinpoint with the target, the height finding with the radar system, and that also determine the bearing with the must-have of the beam. This is very narrow in both the vertical and horizontal plane. Electronic elevation scanning pattern with the search of the radar is set illustrated in Figure 110. Lines originating from the antenna indicate the number of the beam position required for the complete elevation coverage of the practice of the beam overlaps slightly to prevent any gap within the coverage. Each beam position corresponds with a slight change with either the frequency phase of the radiated energy, the change with either the phase of the frequency of the energy covered with the lead of the antenna, different angle with the frequency, or the phase of the major determined to create the only orderly scanning pattern with the convergence of the entire vertical plane electron scanning permits. The automatic compensation on unstable radar platform site with respect to the ship and see the error signals and the produce of the roll and pitch for the ship of the area correct with the radar beam to ensure the complete elevation coverage. Show the Figure 110 show the electronic elevation scan. Mechanical elevation scan is achieved with the mechanical moving the antenna radiation source for the weapon control tracking radar system. Commonly used with the mechanical elevation scanning technique. Most accurate electronic scan radar systems are used with the search radar. Some of the older search radar systems are used with the mechanical elevation scanning device. However, they are being replaced with electronically scanned radar tie systems. Alright, your target resolution. Target resolution is the ability to distinguish between the target with a very close together either range or bearing with the weapons control radar with the required with greater precision. Should be able to distinguish between the target with the only yards apart with the search radar. Search radar is usually less precise with the only distinguish between targets with 100 yards, even miles, even miles per part. Resolution is usually divided into two categories: range resolution, bearing resolution. Range resolution is the ability of the radar system to distinguish between two or more targets with the same bearing with a different range. But the degree of the range is resolution depends on the width of the transmitted pulse, the type of the size of the target, the efficiency of the receiver, the indicator of the pulse width, the primary factor of the range resolution. Well, designed radar system with all the other factors for the maximum efficiency should be able to distinguish the target separated with one half of the pulse of the width of time. Therefore, the theoretical range solution of the radar system can be calculated with the following formula: range resolution in yards over the pulse width of microseconds over the divided by 2 times 328 yards per second. The above formula is often written as range resolution equal to the pulse width times 164 yards per microsecond. For example, the radar system of the pulse width of 5 microseconds, the range resolution is calculated as follows: range resolution pulse width 5 times 164 yards per microsecond. The 820 yards, and above the example, the targets the same bearing that would have the separate with more than 820 yards show for the two targets of the indicator. Bearing resolution. Bearing and zoom in the resolution built with the radar system search separate with the object same range but different bearing. The degree of the bearing resolution depends on the radar beam with the width of the range with the target with the range of the fact of the bearing with the resolution because the radar beam spreads out and the range that increases the radar beam to define with the width of the terms of half power points at the point off the center line between beam with the 1/2 power with the level that the center is plotted with the defined with the bearing beam width. The half points of the connect with the antenna by the curves such as shown in Figure 111. The resulting angular with the width of the curves called the antenna beam width. The physical side of the shape of the antenna at the time remembers the beam width. Beam width can vary from 1 degree to up to 60 degrees. Within Figure 111, only the target with half the power points will reflect the useful echo with the two targets at the same range will be separated at least one beam width to distinguish the two objects. Show the antenna the half power points, the back beam axis, maximum power beam width. Radar accuracy is the measure for the ability of the radar system to determine the correct range of the bearing. In some cases, the height of the object, the degree of the accuracy primarily determine the resolution radar system. Some of the additional effect of the radar accuracy of the pulse with the shape of the atmospheric conditions, pulse shape, and the shape of the pulse radar with the shape of the width of the radio frequency pulse with the equivalence of the minimum range, the range accuracy, the maximum range, the ideal pulse, the shape of the square wave, having vertical leading with the trailing edge. However, the equipment is not usually produce the ideal waveform. The factor influencing minimum range to discuss first. See if the receiver cannot receive the target with the reflection of the transmitter operating. You should be able to see with the narrow pulse with the necessary with a very short range. A sloping trailing edge that extend with the width of the transmitter pulse, although at the end of the vertical, very little with the total power generated. Therefore, all along with the narrow pulse, the trailing edge should be narrow vertical as possible. The sloping edge also affects the minimum range as well with the range accuracy site with provided no definite point, with which means the elapsed time of the indicator time base with the chart of the lower edge of the pulse leading with the wedge will increase the minimum range of the chart point high up with the slope of the lower due to the accuracy range measurement of the short ranges are so vital for the accurate solution of the firing control problem. Maximum range influence of the pulse width of the pulse repetition frequency of the target can reflect with a very small with the transmitted power with the greater transmitted power with the greater with the strength of the echo that could be received with the transmitted pulse should quickly arrive at the maximum amplitude remaining in the amplitude of the duration desired pulse the width of the decay of the instantaneously zero. Figure 112 that illustrates the effect of the pulse shape. So the good and the bad accuracy required with the sharp leading edge, the good and short minimum range required with the sharp trailing edge. Then show the good and maximum range required with the flat top pulse of the sum of the duration and the range of the resolution arrow pulse. Atmospheric conditions. Electromagnetic wavefront with the travel of the empty straight with the straight line with the speed of light, but with the refractive index of the atmospheric effect of both the travel and speed of the electromagnetic wavefront path followed by the electromagnetic energy of the atmosphere, whether direct with the reflective usually slightly curved with the speed of the effect of the temperature, atmospheric pressure for the amount of the water vapor present in the atmosphere, which also has effect of the refractive index of the altitude and increase the combined effect of the influence of the normal atmospheric conditions, usually small but uniform, increase of the single speed, increase of the speed of the travel path of the curve of the slightly downward shown figure 113. Downward curve of the extent of the radar horizon beyond the line of the tangent over the Earth in illustrating figure 114. Alright, shows A and B in path of the signal or surface wavefront path. Shows 114 extension for the radar position, altitude 3,000 feet, optical line outside of the radar over the side of the optical 57.77 miles radar, given with the weather condition 77.3 miles. The region for the downward curve is illustrated with the figure 1B with the figure 113. The line A and B represent the surface of the wavefront with the point A higher to the altitude of the point B with the wavefront A and B with the move with the point with the represent with the A and B speed at A and A is faster than the speed of the B is since the A and A is greater than the altitude. Therefore, given the time of the upper part of the wavefront moves farther than the lower part of the wavefront leans slightly forward, it moves in some of the direction of the propagation always perpendicular to the surface of the wavefront tilted the wavefront called the energy point of the curve downward. Refraction is bending with the electromagnetic wave called with the chain with the density with the medium through the wave that passing with the visible example of the electromagnetic refraction that pairing with the displacement underwater of the object with the bending with the light with the path through the atmosphere with the into the water with the index refraction has been established, which indicate the degree of refraction bending of the call with the difference in substance because of the density of the atmosphere chain with the altitude with the index for refraction chain with gradually with the height. The temperature of the moisture content of the atmosphere normally decrease with the uniform and the increase of the altitude. However, the under certain condition with the temperature may first increase with the height, for then begin with the degree of the situation called with the temperature inversion, and even more with the important the deviation normal may exist over the ocean surface of the atmosphere to close with the surface over the large, but over the water may contain more than normal amount of the moisture content may be decreased with the rapidly height just above the sea. The effect is referred to as the moisture lamps, or the earth temperature, either temperature inversion of the moisture lamps alone with combination can also a large change of the refraction index for the lowest few hundred feet of the atmosphere. The result of the greater bending of the radar waves passing the abnormal condition. Increased bending in such situation referred to as ducting may greatly affect the radar performance. The radar horizon may be extended with the reduced depending on the direction of the radar waves are bent. The effect of the deducting of the radar waves is illustrated figure 115. Deducting effort of the radar waves: warm, cold air, normal range surface duct, the actual range, and no duct action. Another effect of the atmosphere of the radar performance called the particles that suspended in the air with the water droplets, dust particles that diffuse the radar energy with the absorption and reflection scattering, so that the less of energy struck the target. Consequently, the return of the echo is smaller. Overall effect of the reduction of the usable range vary widely. Even the weather condition, high frequency of the radar system, the more is an effect of the weather condition of rain cloud with some part of the world does suspend with the can greatly decrease the normal range of high frequency radar. High frequency radar. Alright, your radar principle of operation. Radar systems, like other complex electrical systems, are components of major subsystem of any individual circle. This section introduces your major subsystems common to both of the radar system. Brief functional description of subsystem principles of operation will be provided. As much more detailed explanation of radar subsystems will be given in chapter 2 and 3. Some of the most radar systems used today, some of the variation pulse radar system units discussed in this section will be the pulse radar, and all other types of radars. Some of the variations of each unit, but the variations will be explained as necessary. Radar components. Pulse radar system can be functionally divided in 6 essential components as shown in Figure 116. These components are briefly described in the following paragraphs and will be explained in that detail afterwards. Alright, your duplex system, the power supply going through the transmitter, synchronizer, receiver, indicator. Your duplex system goes to the receiver, the transmitter going, and the synchronizer and transmitter going to duplex, and then your receiver going to indicator. Synchronizer also refers to the timer key over the supply with the synchronizing signal to transmit the pulse of the indicator, otherwise associated circuits. Transmitter generates the electromagnetic energy form a short with powerful pulse of the duplex allowed with the same antenna with the transmitter receiving. The antenna system in the route of the electromagnetic energy of the transmitter radiates it into the highly directional beam. The receiver, the returning echo, the rotates routes the echo to the receiver. The receiver amplified the weakening electromagnetic pulse of the return of the reflecting object will reproduce the video pulse and they are sent to the indicator. The indicator produces the visual indication of the equal pulse of the manner at a minimum furnished the range of bearing information. Well, the physical configuration of the radar system for the aim of the radar system will be present with the functional block diagram Figure 116. With the actual radar systems may have several of their functional components, but the one physical unit, one single unit of each function may record several physical units. With the functional block diagram in the basic radar system, radar set may be used to analyze the operation of almost any radar set. And the following paragraph is a brief description of the operation of each of the major components in the given. Synchronizer. The synchronizer ensures that all the circuits connected with the radar system operate at the defined time of the relationship, but also the time of the interval between the transmitted pulse to ensure the interval of the proper length with the time pulses also to ensure the synchronizing circuit operation are related to the pulse rate frequency. The pulse rate with frequency can be set with a stable oscillator such as the wave oscillator, multi-vibrator, and blocking oscillator. Upwards and then applied with the pulse shape in the circuit with the provided time produced timing pulses associated with the components can be timed. The output with the synchronizing timing signal will be a transmitter at the turned on transmitter. The transmitter generates powerful pulse with the electromagnetic energy precise interval of the required power with the obtained with the high power microwave oscillator sorts. So for the magnetron with the microwave amplifier such as the klystron that is applied with a lower power for radio frequency so for the construction and operation microwave component that can be reviewed in Neets Module 11. The microwave principle of the higher power generator with an oscillator amplifier requires operating power with the form of the properly timed highly amplitude rectangular pulse of the most supplied with the transmitter until they call the modulator. The high power oscillators use the modulator high voltage pulse switch for the oscillator on and off supply of the high power electromagnetic energy. The microwave power amplifier is used the modulator pull activate the amplifier just before the arrival of the electromagnetic pulse form a preceding stage of the frequency generation source normally because of the extremely high voltage involved. Modulator or pulses supplied with a cathode power tube then plate with ground with a potential shield personnel for a shock hazard. Modulator pulse may be more than 100,000 volts in high power radar transmitter. In any case, the radar transmitter produces the voltage current radiation hazard with extreme dangers to personnel. Safety precautions must always be strictly observed when working around radar transmitters. The duplexer is essential with the electronic switch of the permanent of the radar system. You with the signal antenna of the bulb of the transmitter with the receiver. The duplex must contain the neck of the antenna of the transmitter, the disconnect of the antenna of the receiver, the duration of the transmitted pulse. The receiver may be completely isolated transmitter with the avoid damage of the extreme sensitivity of the receiver, the input circuitry, but after the transmitted pulse has in with the duplexer must rapidly disconnect with the transmitter and connect the receiver to the antenna with the previously mentioned with the switching time and scope of the receiver cover time, and it must be the very fast. If close-in targets are detected, additional duplexer should be absorbed with very low power during either phase of the operation. Low loss character for the particularly important during the receive period of the duplexer operates because of the receive signal with extremely low amplitude. For your antenna system around the pulse of the transmitter radio with the direction being taken with the returning out of the pulse of the receiver with the minimum loss of the antenna system. Include the antenna transmission line waveguide with the from the transmitter to the antenna, the transmission line with the waveguide for the antenna to the receiver. Some complication of the duplexer is included as a component of the antenna system. You receive the receiver to accept the weak echo signal of the antenna system of the amplified detect with the pulse envelope of the amplifier with the pulse then route to the indicator. One of the primary functions of the radar receive the convert with the frequency, receive the echo signal of the lower frequency that is easier to amplify because the radar frequency is very high with the difficulty to amplify the lower frequencies called the intermediate frequency with the type of the receiver the ease of the frequency conversion technique. Super heterodyne receiver the super heterodyne receiver the radar system the most have the goodly stable extremely sensitive to stabilization ensure with be careful design overall sensitivity greatly increased by the use of the intermediate frequencies. Indicator. The indicator uses the received signal with the route with the radar receive the visual indicator from the target information with the cathode ray oscilloscope with the ideal instrument with the presentation radar data with the because they only show the variation signal quantity so the voltage but also give the indication relative to the value with the two more quantity with the sweep frequency with the radar indicator is determined the pulse repetition frequency of the radar system. Sweeping duration is determined by the setting of the radar selection range selector switch. These indicators similar to the oscillator term with the radar scope of the common with the referring radar indicators. Alright, scanning. The radar system often identified with the type of the scanning system with the scanning of the systematic movement of the radar beam with the definite power pattern searching with the tracking the target. Type of the method of scanning depending on the purpose of the type of the radar. One on the antenna side of the design. In some cases, the type of the scan will change the particular system of the mode of the operation. For the example, the particular radar system search mode may be quite different from those of the track module scan. Mode scanning. Stationary lobe scanning. Single stationary lobe scanning system. The simplest type of scanning with a method to produce a single beam with a stationary relationship to the antenna. The antenna then mechanically rotated continuously to obtain through complete 368 azimuth coverage of the stationary lobe. However, they cannot satisfactorily track moving the object because it does not provide enough information about the object's movement to the operation automatic tracking circuit is of the fire control track. Radar two-dimensional. The search for the radar, however, does not use a single lobe with a standard 360-degree panel. The cover the automatic tracking circuit that are not usually within 2D radars. Alright, your single lobe scanning is unsuitable for the use of the tracking radar. Several reasons. For example, the letter assume that the target somewhat with the lobe axis with the receiver the detection signal with the reflect with the target. If the reflected signal begin with the degree with the strength with the target like with the shown but off with the lobe axis. In this case, with the beam, and there must be a move with the continuing tracking. The beam might be moved with the operator tracking the target with the optical side with such as slow with the inaccurate limited with the condition of the visibility automatic tracking system would require the beam to scan the search for the target in such case. Again, assuming the missiles are riding on the following axis, single beam with the strength of the singular receive the beam with the radar receive the missile will gradually decrease the distance from transmitter increase the signal. If the signal strength decreases slowly, the missile will know with the built-in with the detection system circuitry with no longer the axis for the lobe, but will not know which way of the terminal to get back to the axis. The symbol beam does not contain enough information in missile guidance. Alright, method of the beam scanning. Two basic methods of the beam scanning are mechanical, electronical. Mechanical scanning of the beam can be moved with various ways. The entire antime can be moved with the desired pattern, but the energy field of the source can be moved with the relatively fixed reflector. The reflector can be moved with the relatively fixed source of the electronic scanning beam and is effectively moved by such means of the switching between the set of the feeder source of the varying of the phase of the elements of the multi-element array. Through the comparing altitude, the phase difference between the single receiver of the multi-element array, the combination of mechanical electronic scanning is also used in some antenna systems. Mechanical scanning. The most common type of the mechanical scanning is the rotation of the antenna with 360 degrees about obtaining the azimuth of cover. The most search for the radar set with the method of the common scanning with the target tracking the missile beam radar system of the conical or cone-like scanning with the general accomplishment mechanical nucleating radio frequency feed point. Nucleation, the difficulty to describe the word is easily demonstrated by how with a pencil in two hands while the holding the eraser there's still possible. The swinging point, the circular motion with the pencil is referred to the rotation pencil point correspond with the opening with the transmitter at the end of the waveguide into the important fact of the remember the polarization of the beam does not change during the scanning of the cycle of the mean for the axis of the moving the feeder does not change with either horizontal vertical orientation when the feeder is moving. You might compare with the feeder moving to that of Ferris wheel with the vertical orientation. Each of the sets receipt remains with the same regardless of the position of the wheel. Recall the waveguide with the metal pipe, usually rectangular cross section, used to conduct with the radar frequency energy for the transmitter into the antenna, open end of the wave phase for the concave side of the reflector of the radio frequency energy. Emitted to the balance of the reflector surface of the canonical scan can be generated with the nucleation of the waveguide with the process of the axis of the waveguide itself moved with the special small conical pattern actual installation of the nucleating waveguide with third dimensional movement of fast and small amplitude with the 10 and observer of the waveguide appear more merely like the vibration slightly. By moving the eve of the waveguide of the antenna, you generate the canonical scan pattern is shown in Figure 117. The axis of the radar lobe is made with the sweep out with the cone and space of the apex of the cones, and of course the radar transmitter of the antenna reflector, any given distance from the antenna. The path of the lobe axis is a circle with the use of the range of the beam and the inner edge of the lobe always overlap the axis for the scan. Show for the 117 the canonical axle, the potent path of the lobe axis for the scanning. Now assume that you have the canonical scanning beam with the target track with the target of the scan, the axis of the train with the reflected scan signal to remain with constant of the chain with gradually with the range of the changes, but if the target slightly off the axis of the amplitude of the reflected signal will change with the scan rate. For example, if the target left on the scan axis that's shown figure 118 with the reflected signal will meet the maximum strength of the lobe sweep with the left part with the cone within the signals will quickly decrease the minimum of the lobe sweep with the right part with the information instantaneous position of the beam of the relative of the scan axis one on the strength of the reflected signal and fed to the computer. So this computer and the radar system refer to the angle tracking the angle servo circle of the angular error detector the target the move of the off the scan axis of the computer instantly determines the direction amount of the antenna movement that required for the continuing tracking. The computer output is used to continue servo mechanisms to move the antenna in this way the target is tracked accurately and automatically. Shows the path of the beam direction 0, 270, 90, 180 degrees, reflected signal strength, electronic scanning. Electronic scanning can be accomplished with low motion rapidly without the inherent maintenance of the disadvantage of the mechanical stiffness because the electronic scanning cannot generally cover the large area of the area space, but sometimes combined with the mechanical scanning particular applications. The monopole simulation and opening of the all range bearing with the elevation angle of the information of the target is obtained with a single pole with the monopole with the scanning with the fire control tracking radars. For target track with the radar, discover the produce with the narrow circular beam with the poles the radar frequency at the high pulse repetition rate. Each pulse is divided into 4 signals which are equal both in the amplitude of the phase. The 4 signals are at the same time for each of the 4 feed horns that are grouped into this cluster. With the result of the radiated energy is focused into the beam of the microwave lamp. The energy reflected from the target that refocused by the lens back into the feed horn, but the total amount of the energy received by each of the horn varies depending on the position target level of the beam axis. The illustrated figure 119 for target a different position with the reflect in respect with the beam axis. Note that the phase of the inversion taken place for the microwave lens is similar to the image inversion that's taken place for the optical system. Shoot for the target above the line of sight with the ABCD horns, and then ABCD horns and monopulse scanning. Target below the before sight line, turn above the bore sight line, turn to the right of the bore sight line, turn to the left of the bore sight line. The amplitude return signal and receive with each of the horn continuously compared with the receive with the other horn with each signal with the generator that indicate the relative position with the target the respect of the axis of the beam. All servo those circle the receive of the arrow signals correctly position on the radar's beam. Keep the beam axis and then target the transverse bearing signal may be the signal of the horn A added to the C form, horns B added to D waves. So there's a guide to design some of the B and D with made over the 180 degrees outside, but the sum of the A and C with the 2 are combined with the transversal signal difference of the A plus C minus B plus D signal sign that the sense of the horn is position figure 119. The relative of the amplitude of the horn circle give the indication of the magnitude of the transverse over the elevation signal. Consider the signal over the horns of the CD add with the 180 degree over the horn A and B with the A over the bracketed A plus B minus C plus D with the sum of the range and signal of the component with the signal from the feed horns with the added together the favor the provided with the reference from the target direction center of the beam axis of the measure with the terrain signal that is used of the phase reference the transverse elevation error signal. Transverse elevation error signal compared with the radar receiver with the range of the reference signal of the output of the receiver may be either positive with the negative pole with the amplitude with the pole the proportional with the angle between the beam axis with the line drawn on with the the proportional polarity of the output signal they indicate with the target is bubble over the right over the left of the beam axis for the core for the target is directly in line. So for the output of the receiver the 0 for the non-angle the tracking error is produced. Important advantage for the monopole tracking radar over the radar. You for the canonical scan the instantaneous angular move measurement are not subject to the errors to errors called the scintillation. Scintillation can occur with the target maneuvers or moves. Radar poles bounce off of the different areas of the target that are called the random reflective. They may leave with the tracking error. The monopole tracking radar is not subject to the type of the error because of each of the poles provide the angular measurement without regard to result of the pulse train when they know such cross section fluctuation can affect the measurement. In addition, the advantage of the monopole track with the mechanical action is required. Electroscanning and with the search radar system is explained with the general terms earlier with the chapter during the discussion. Elevation cover the type of the electronic scanning is often called frequency scanning. The depth of the explanation frequency scanning theory can be found in the fire control technician's rate and tech training manuals. Radar transmission method. The radar system normally divided into an operational category. Based on every transmission from the method that used up to this point, we moved. I mentioned the pulse method of the transmission illustrates the basic radar concepts. Also, pulse method, the most common method of the transmitting radar energy. Two other methods sometimes used in special applications: the continuous wave method and the frequency modulation method. All 3 basic transmission methods are often further subdivided and designated with specific variation combination. Continuous wave method. Radio frequency energy transmitted at a fixed point with continuously instructing the object that it is either moving toward or away from the source of the energy. The frequency is reflected with the energy of the chain of the shift. The frequency is known by the Doppler Effect. The difference of the frequency between the transmitted reflected energy indicated on both the presence and speed of the moving Talk about the Doppler Effect. A common example of the Doppler Effect for the action of the chain with the pitch of the whistle of an approaching train with the whistle appear with the chain with the pitch of the high tone of the train approach to the lower tone. They move away from the observer. Train approach with the apparent increase of the frequency with the increase of the pitch is heard. The train moves away with the apparent decrease of the frequency with the decrease of the pitch is heard. Pitch variation is known by the Doppler Effect. Let's explain the reason for the apparent change with the pitch. For the assume the transmitter emits the audio signal with the frequency with the 60 Hz. The transmitter traveling at a velocity of 360 feet per second at the end of the 1 second. The transmitter move from point P to point 1 P1 is shown in figure view A. Figure 120, the total distance to point P with the observer at 1,080 feet with the velocity of the sound of 1,080 feet per second. The sound emitted at the point P will receive the observer at 1 second and 2 with the final length of the transmitted signal. You divide the velocity of the signal with 1,080 feet per second by the frequency of 60 Hz. The result of 18 feet is shown below. The wavelength over the velocity of the frequency 1,800 feet per second over 60 Hz is 18 feet. Show the observer point 1, 360 feet, 720 feet, 1,080 feet, point 1 and point 2 observers 360 feet, 1,080 feet. If the second transmitter move at 360 feet, the transmitter at the 60 Hz and the 1 second of the first cycle of the transmitter, the single reach for the observer, just the sixth cycle is learning the transmitter at the point P1 of these conditions. 60 Hz emitted is located with the observer at point P1 and note for the distance of only 720 feet, 1,080 minus 360 feet Hz for the spread over the distance from the point P1 to observe the wavelength of just 12 feet. The 720 feet divided by 60 to find new frequency following the frequency of the velocity over the wavelength. You'd have 1,180 over 12 and 90 Hz. Original frequency of 60 Hz has changed with the apparently frequency of 90 Hz. Now the frequency only applied with the observed note of the Doppler effect. For Doppler frequency variation is directly proportional to velocity approaching transmitter. The faster the transmitter the move forward for the observer, the greater the number of the wave that will create in the space between the transmitter and the observer. Of the transmitter were stationary observer, the moving of the approaching the transmitter of the observer would be encountered with a wave of the per unit, with the result of the observer would hear the higher pitch that the end transmitter would actually emit. If the transmitter were traveling away from the observer, shown the UB. The figure 120, the first cycle would leave with the transmitter at point P with the sixth at the point 2, with the first cycle would reach the observer, the transmitter reach point 2, but would receive the 60 cycle stretch over the 1,080 plus 360 feet, the total 1,440 feet with a wavelength with a 60 Hz of 1,440 feet divided by 60 is 24 feet. The parent frequency 1,080 divided by 24 is 40 Hz. The use of the continuous wave Doppler system. The continuous wave Doppler system uses the sub of the wave on one radar were applied with the radar set. The difference between the transmitted and the reflected wave that determine the speed of the moving object. The Doppler method is best made for detecting fast moving objects that do not require range. The resolution as moving objects approach with the transmitter, they can count with the reflect with the microwaves per unit over the time, and the amount of the frequency shift produced is very small with the relation to the carrier frequency. This is because of the velocity of the propagation signal is very high compared to the same speed with the touch. However, the because of the carrier frequency used for the radar at high with the larger frequency shift, the auto frequency range are produced with the amount of shift with the proportional speed of the reflecting object with the 1/4 cycle with the shift with the 10,000 MHz for the provided speed measurement accurate with the fraction with the present percent. If the object of the moving velocity relative to the radar can be detected with comparing with the transmitter, the frequency of the echo frequency, the difference for the because of the Doppler shift, the difference of the brief frequency, sometimes called the Doppler frequency, is related to the object velocity. The separation background radar contact is based on the Doppler frequency that it causes the reflection of the signal of the moving object with this amount. With the disadvantage of the Doppler shift, or that it does not determine the range of the object, nor is it able to differentiate between objects when they lie in the same direction or are traveling at the same speed. Moreover, it does not stationary slowly moving object. The pulse radar system can be detected. To track an object over the continuous wave of Doppler, you must determine the radar range of the Doppler frequency that is not directly related to the range of the another method to determine the object range using two separate transmitters of the Doppler with the two different frequencies, frequency 1, frequency 2, determine the range of the measuring relative to the phase of the difference between two Doppler frequencies. In such system, mixed layers you combine the two transmitted frequencies separate with the two received frequencies. This permits that use of one transmitting and receiving antenna. Instead of using two transmitter frequencies, you can find the range of the sweep within the transmitter frequency uniform with the time covered the frequency range of the frequency 1 and frequency 2. The beat of the difference of frequency between the transmitter and receiver signal is a functioning range for the in this type of the radar. The velocity as well, but the range is measured. Alright, your frequency modulation method. The frequency modulation method transmit radio of the radio frequency wave, the frequency of the radio frequency wave continuously increasing the fixed reference frequency at any of the of the frequency determine the signal, the difference for the frequency of the radiated signal. The different frequency determine the time it took for the signal to travel the distance from the transmitter to the object. Example, the frequency modulated of the signal plotted against the time. They shown in figure 121, shown in the figure 420 MHz with the frequency increased with the inline linear with a 460 MHz with the quickly drop at 420 MHz. Again with the frequency drop at 420 MHz. The frequency cycles are start over again. Show the frequency modulation chart time interval 0 to 1 and 7 microseconds in thirds. Frequency 1 and 420, frequency 2, 460, frequency at negative 20 megahertz. Frequency ranging with the chamber of the 40 megahertz for the respect of the time, and therefore it will vary with any time during the cycle of the camera with the base for the commuting of the time and length after the start of the frequency of the cycle. For example, the time interval 0 and transmit the same with the 420 megahertz signal time toward an object with the strike for the object for the return with the receiver the transmitter time interval 1. Transmitter is then out with a new frequency with the 440 megahertz for the time interval 1, 420 megahertz for the return signal. The 440 megahertz transmitter signal is fed to the receiver simultaneously with the two signals are made with the receiver. The beat frequency result of the beat frequency varies directly with the distance of the object with the increase of the distance and increase with the using information calibrated the device measure for the frequency indicating range. The system works well with the detect with the object with the station with the aircraft altimeters for the given the continuous reading with the head above the earth and the aircraft. The system is not satisfactory for the locating the moving object. To recover the moving targets produced with the frequency shift the return signal to recover the Doppler effect with the effect for the accuracy of the range measurement. Alright, pulse method modulation method. The pulse modulation method of the energy transmission will analyze to some of the example earlier with the chapter of the previous discussion indicate the radio frequency energy that can be transmitted in very short bursts called pulse. These pulses are extremely short time duration, usually an order of 1/10 of a microsecond with approximately 50 microseconds within the method of the transmitter. Determine the wave for the very short time the pulse radiation frequency energy is transmitted. Is shown in view A, figure 122, where the transmitter is turned off with the pulse travel outward with the transmitter into the receiver, the light with the view B with the pulse strike with the object with the view C, reflected to begin with the travel the back of the toward of the radar system and still moving the same velocity. View D with the pulse and then receive with the radar system. View E, the interval between the transmission and reception is computed with the converted into a visual indication of the range for the miles and yard of the radar cycle is started over again by transmitting another pulse. View F, the method does not depend on the relative frequency of the return signal on the motion of the target, therefore it's an important advantage of the continuous wave and the frequency modulation method. Shift the emanating pulse to 628 yards pulse detection pulse Doppler method. Alright, the pulse radar system must modified with the use of the Doppler effect with the detect with the moving object requirement, the Doppler radar effect with the coherency of the Doppler radar with the coherency of some of the definite phase relationship must distinguish with the transmitted frequency radio reference frequency which of the you with the detect with the Doppler shift with the receiver signal with the moving object with the detect with the phase the difference between the target signal background noise component of the phase detection from the type of the reliable coherency between the transmitter frequency and the receiver reference frequency. The coherent detection from the stable the continuous wave reference oscillator signal that was locked in phase with the transmitter during each of the transmitted pulse mixed with the echo signal to produce the beat and difference signal with the symptom the reference for the oscillator transmitter is located in the phase of the echo the effectively compared with the transmitter frequency phase. The phase relationship with the echo, the fixed object with the transmitter constant, the amplitude of the beat signal remains constant. The beat signal varying amplitude indicates the moving object with the basic with the phase difference between the reference oscillator signal and the echo signal exchange with the range of the rectified reflecting object chamber. The constant amplitude of the beat signal is filtered out with the receiver. The best beating signal is varying amplitude and the same with the radar indicator oscilloscope of the display. Alright, your radar classification and use. The radar system, like however, come in the various sizes, however, the different performance and specifications. Some of the radar than you with the air traffic control of the airports are other than you with the long-range surveillance, early warning systems, radar systems, and however the municipal guidance system, small portable radar system can be maintained with operated with one person available. The export weapons system occupies several large rooms. Military classification radar system, the large number of the radar systems you with the military have force for development of the joint service classification system accurate identification. Federal Aviation Agency also makes sensitive use for the radar system commercial aircraft in flight and landing control, but not use with the military classification system radar system use classified according to the specific function installation vehicle. Some of the commonly used is search for the ground and land based track airborne height and finder shipboard. Joint service standardized classification system further divided into the broad categories for more precise identification. Table 1.1 listing with the equivalent identification indicator that use the table to identify the particular radar system. Illustrating figure 123. Note that the simplicity the only portion of the table that has been used illustrated. So the installation of the first letter, the second letter, type of equipment, purpose for the third letter, and miscellaneous identification, and 123 shows the joint classification service the Army Navy installation type and the module number purpose. Radar functions. No single radar system has yet been designed that can perform all of the many of the radar functions required by the military. Some of the newer systems that combine with the several functions that formally required by the individual radar system, but no single system fully required by the men of the modern wherefore, as a result of the modern warship, aircraft, shore stations usually have the several radar system that each of the particular performing a different function. One radar system called the search radar designed with the scan with the volume of the space that provided initial detection of all the targets of the search radars, almost always detect with determination position of the new target with later track radar. Track radar provides with continuous range bearing the elevation data with the one or more target with the most radar system, either its military and one of the other two categories with their individual radar system very design capability. Some radar systems are designed specific function that do not precisely fit into the either of the above category of the radar speed. Going with the example, the radar is designed specifically to measure speed of the target that measure either the much more complex the radar system that adapts to detect with the only fast moving target with the for the aircraft. Since aircraft usually move faster than the weather, and so it's target the velocity sensitive of the radar, but they can eliminate unwanted clutter with the radar indicator the radar system, and then detect with the process that only moving targets called the moving target indicators, or MTI, are usually combined with a conventional search radar. Another form of the radar widely used by the military and civilian aircraft with the radar altimeter on some of the surface of the base of the radar to determine the height of the target of the airborne radar that can determine the distance of the aircraft to the ground. Any aircraft with the radar determine the height of the above the ground radar altimeters with the frequency modulated signal type that I described earlier in this chapter. Alright, radar type. The preceding paragraph didn't give the radar system divided into types based on the design of the section. The section generally character for the several common use of the radar system. Typical characteristics of the radar and special character for the in particular radar system. Search radar of the previously mentioned continuously scanning the volume scan with the provide initial detection of all the targets within the space of the radar search system that are further divided into specific special types of the type of the object design tech. For example, surface search, air search, or height finding radars, all types of search radar. Alright, the surface search radar system has a numeric function of detection determination accurate range of the bearing with the surface object with the low-lying aircraft, the maintenance of a 360-degree search over the pattern of the whole object with the line of sight with the distance of the radar antenna. Maximum range ability with the surface search radar of the primary limited with the radar horizon, and therefore the higher frequency with the permit with the maximum reflection small with the reflecting area search with the smash ship mass head, strict with the periscope of the submarine with the narrow pulse with the width that you would permit the higher degree of the resolution with the short range they achieve with the greater range accuracy with the high pulse repetition rate that you would permit maximum definition of the detected object with medium peak power that can be used as permit the detection of a small object with the line of sight of the distance of a vertical beam in which for the permit compensation pitch roll the own ship detection from low-flying aircraft. Now, narrow horizontal beam width may permit the accurate bearing determination, good bearing resolution. For example, the common shipboard server each of the radar following the design specification transmitter frequency 5,450 to 5,825 megahertz, pulse width quarter to 1.3 microseconds. Of the pulse repetition rate is between 625 to 650 pulse per second. The peak power with 190 to 285 kilowatts. Vertical beam width of 12 to 16 degrees. Horizontal beam 1.5 degrees. Your surface search radar you detect with the presence of the surface craft with low line flying aircraft to determine the presence of the ship. Surface radar refers to provide with the type of the information input of the weapon system and specifically engagement hostile targets. Provide the fire control radar with the ship surface with the search radar used extensively as navigational aid of the coastal waters and poor weather conditions. Typical surface search radar intended shown figure 124. Or your air search radar. Air search radar initially detect with the determine with the position course with the speed of the air target with the relatively large air with the maximum range of the air search radar can see 300 mile with the bearing air coverage of the complete with the 360-degree cycle of the air search radar system usually divided into two categories with the base on the amount of the position of the information supplied. Mentioned earlier with the chapter radars have provided only range of the bearing information referred to in two-dimensional or 2D radars. Radar set with the supply range of the bearing height they call the three-dimensional and 3D radar. 3D radar will cover the next section of the covering pattern of the typical 2D radar system as illustrated in figure 125. Typical 2D radar air search radar shown in figure 126 show the 360-degree antenna vertical beam width or horizontal beam width. Show the 2D air search radar relatively low transmitter frequency with the 2D search radar with the permanent long range of the transmission minimum actuation weight wide pulse width with a high peak power usually used a detection small object with greater distance low pulse repetition of the selective with the permanent the greater maximum range wide vertical beam with either ensure the detection object with the surface with relatively high altitudes compensate with the pitch and roll with their own ship the output of the characteristic air research and the classified therefore will not have to discuss. Air search radar systems usually with an early warning device together they can detect with the approach of the enemy the aircraft with the greater distance and hostile situation. Early detection of the enemy is vital for the successful defense against the attack. Anti-aircraft defense for the formerly shipboard guns and missile for the fire of the plane with a high degree of the readiness at the time of the repel, the attack, the range of the bearing information provided by any with the air search radar of the initial position of the fire control tracking radar on the target. The function of the air search radar system guiding combat air control of the aircraft due to the positional stable the intercept of the enemy aircraft. The key for the aircraft control of the guidance information is obtained the radio operated passive of the aircraft either by a voice command, voice radio, or computer link with the aircraft. Alright, your height finding search radar. The primary function of the height finding search radar, height finding radar is sometimes referred to as 3D radar with a computing accurate range of the bearing altitude of the aircraft. The target is detected by air search radar, but the height finding radar that's used for the ship, the air control, the compute, sometimes called the combat air patrol of the aircraft during the interception of the air target with the modern 3D radar. It's often used with the primary air search rating radar figure 127, but because of the higher accuracy, the maximum ranges are only slightly less than those available to 2D radar. So for the 3D air search radar, the range is incapable of the 3D search radar, limited to some extent the operating frequency that is higher than 2D radar. Disadvantage is particularly partially offset by the higher output with the pipe beam with the width of the narrow both vertical and horizontal plane. The 3D radar system transmits the several narrow beam with the optional obtaining altitude coverage for the frequency compensation roll and pitch must be provided with the shipboard installation to ensure the accurate heighting of the information. Application of the height finding radars include the following: obtain range, bearing, and altitude data during the enemy aircraft missiles to assist the control of the air patrol aircraft, detecting low flying aircraft to determine the range, distance, and low land masses. Tracking aircraft over land, detecting certain weather phenomena, tracking weather balloons, providing precise range, bearing, heighting information to the fast, accurate, and initial positioning of the fire control tracking radars. Alright, tracking radar. Radar that provides continuous positional data of the target is called the tracking radar. Most tracking radar systems use the military for the fire control of the two names. They're often used with the interchangeable fire control tracking radar, usually produced the very narrow circular beam fire control radar must be detected with the general location of the desired target because of the narrow beam of the pattern of the scope of the destination phase of the equipment of the operation. Once the general vicinity of the target of the radar system switch for the acquisition phase of the operation. During the acquisition of the radar system searches a small volume of the space for the prearranged pattern until the target is located. The target is located with the radar system. Enter for the track phase of the operation. One of the several possible some of the scanning technique of the radar system automatically found that all the target motion of the radar system is said to be locked on the target during the track phase of the three sequential phase of the operation. Referred to as the modes are coming to the mode of the target processing sequence for the more fine control radars. Type of typical fire control radar characteristics include the very high pulse rate frequencies, very narrow pulse width, and the very narrow beam width of a character of the width over the process, providing extreme accuracy for the limit of the range of making initial target with a deflection typical fire control radiation antenna shown in figure 128. If the example, the antenna used to produce the narrow beam that covers the protective dome. Figure 128 shows the fire control radar, Doppler receiving the antenna, the guide track antenna, and the capture antenna. Missile guidance radar. The radar system will provide the information with guide the missile with the hardest hostile target to couple the guidance radar with the missile with the radar intercept the target with the three basic of the beam rider missiles. The following beam of the radar is kept with them continually pointed if the desired target of homing with the missile detected at home with the radar energy deflect with the target with the reflected energy is brought with the radar transmitter either the missile the launch point with the detected with the receiving the missile with the read the path of the homing missile the home with the energy that's radiated with the target with the path cover the target position must know all the time the guidance radar the general part of the associated with the fire control tracking radar. Some instances of the three radar beams are required to provide complete guidance with the missile the beam and the riding missile. For example, the must be lined into the beam and then must be routed the beam to the target initially with the wide beam radiated by capture radar to gain the capture with the control of the missile after the missile entered the capture beam the narrow beam is radiated the guidance radar to gather the missile to the target during both capture and guidance operation. The tracking radar continue with the tracking target. The figure 129 illustrates the relationship with the three differential radar beams: radar attention, missile flight path, the capture beam, guidance beam, and track beam. Alright, your carrier controlled approach to the ground controlled approach. The carrier controlled approach to the ground control approach to the systems attached essentially shipboard land-based version of the same type of the radar with the carrier controlled approach to the radar system, usually more sophisticated system over the ground control approach. This is because of the moment of the ship, the more complicated the landing problem. Both systems, however, the guided aircraft are safe the landing with under the condition of approaching zero visibility. But many of the radar aircraft that are detected with observed during the final approach of the landing sequence, the guidance information is applied with the pilot form of the verbal radio instruction on the automatic pilot or autopilot in the form of the pulse control signals. Airborne radar. Airborne radar is designed especially to meet with the strict space with the weight limitations that are necessary for the airborne equipment. That even the airborne radar set to develop the same peak power as a shipboard and shoreboard is set. As the shipboard radar, airborne radar set come with an amazingly mild. There are two severe, many different. The purpose of some of the sets are mounted and blisters and dome, but the format of the fuselage is other than mounted in those of the aircraft and the fighter aircraft. The primary mission of the radar is to aid the search for the interception, destruction of the enemy aircraft. That requires the radar system having tracking after airborne radar. Also have many other purposes. The following some of the conventional classification: airborne radar search, intercept, miscontrol, bombing, navigation, and airborne earlier warning. Summary. Chapter 1.